All right, so mathematicians started working on calculus way back in the 1600s, but it's actually a pretty new math when you think of all the math that's been around. Calculus is one of the newest ones. So what happened was that mathematicians were always interested in finding the area of objects that they couldn't find the area of before. Like, you know, they could always find the area of circles, rectangles. They could find surface area, volume, all that good stuff even back then. But with more interesting looking curves, how can we find the exact area? So what happens is they started estimating. They did those upper sums with rectangles. They did those lower sums with rectangles. And they realized that those were not really that accurate. So they decided, hey, what if we use trapezoids? Is there something that would be better? Can you see how if I'm trying to find the area from 1 to 3, and instead of drawing upper rectangles or lower rectangles, if I draw trapezoids in there, it gives me a pretty good estimate, doesn't it? Trapezoids are much better than rectangles. So the mathematicians that were working on this, they all decided, hey, let's come up with a rule then if we use trapezoids. And this is what they came up with. This is the rule that will find the area of the rectangle, of the trapezoids. Because they didn't want to have to sit here and find the area of this trapezoid, the area of this trapezoid, the area of this trapezoid, etc. That was too much work. So they figured out that this formula will do it to find the area of each of those trapezoids and find the sum of them. So part of being good at calculus is understanding formulas. So this is saying that the integral from a to b of the function is equal to b minus a over 2n. And then we have to plug in the first x, or the first y value rather, plus 2 times the next y value, plus 2 times the next y value, and so on, plus 1 times that last y value. Now, based on this formula, it's saying we have to do f of x sub 0. That means our initial starting value. This says we're going to stop when we plug in that very last value for n. It's a little bit confusing, but this one, we are going to need to find that starting x value and that ending x value. The number of terms that we're going to end up with is always going to be n plus 1. So the number of trapezoids I choose to make. See how I made 1, 2, 3, 4 trapezoids? But I have to use this value of y, this value of y, this value of y, this value, this value. So I have to use all those y values. That's what this is saying. All right, let's look at this and then we'll talk about some other things with it too. Use the trapezoidal rule on the example above for n equals 4. You will need to find f of x for x equals 1, 1.5, 2, 2.5, and 3. So I'm telling you here what x values you need to use. But if I hadn't told you, here's what you would have to do. You would have to do b minus a divided by n, and that's going to tell you your interval. So to find out how far apart these are, I have to do, in this case, 3 minus 1 is 2, divided by n is 4, 2 over 4 is a half. So see how I have to start at 1, I had to add on a half, add on another half, until I get up to this one, until I get up to that top number. Now, here's the whole reason that we need these rules. What if I went and tried to do this problem? And what's another name for 1 over x? So let's say I try to integrate that. If I add 1, what do I get? And I would divide by 0. You can't do it, can you? So this would be a problem that cannot be integrated. So I would have to use trapezoidal or Simpson's rule. All right, so let's look at the trapezoidal rule and see how it will work. So to find the area, I'm using this formula right here. I have to do b minus a. So here's my problem again. So what's b minus a? 3 minus 1 is going to be 2, so I'm going to have 2 on the top, over 2 times n. So what's my n value? 4, so 8 on the bottom. Now it says I have to do f of x sub 0. So I'm going to have to know what these y values are. When I plug in 1, what do I get? When I plug in 1.5, when I plug in 2, when I plug in 2.5, when I plug in 3. See how that's going to give me 5 points? And remember I said you always have to have n plus 1? You always have to start here, then you add on a half, 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 and you have to start with 1 and you have to end with 3. And now I have to plug these into my function. If I plug in 1 to my function, what's 1 divided by 1? What's 1 divided by 3 halves? 2/3. 1 divided by 2? 1 divided by 5 halves? And 1 divided by 3 is right there. So these are my y values that I need to use this formula. So now the formula says I'm going to use my initial f of x. Here's my initial f of x, 1 plus. I'm going to use my next f of x. But what do I have to do to it? Multiply it by 2. So it's going to be 2 times my next f of x plus my next one has to get multiplied by 2, and my next y value is 1/2 plus my next y value has to get multiplied by 2. Now, what about the last one? Does my last y value get multiplied by 2? No. All right, so this right here should give me a pretty good estimate. So we just type this into the calculator now. So we're going to do, this would be 1/4, and then 1 plus, I'm going to go ahead and multiply these, 4/3, plus 2 times a half is 1, plus, that's 4/5, plus 1/3. And here's what I get, 1.12. That's approximately. But that would be the answer for the trapezoidal rule rounded to the nearest hundredth. That's what the area is that I get. Here's what people think. They're like, well, the trapezoidal rule is only an estimate, so I can just give you an estimate. No, the trapezoidal rule is an estimate, but it has an exact answer if I tell you to round it to the nearest hundredth. That's it, right there. Okay. So let's say instead of going from 1 to 3, we were going from 2 to 4. Can you see how that would change then? I would have plugged in 2, then what? 2.5, then 3, 3.5, and 4, right? Okay, if my n value was 4. All right, let's go to Simpson's now. So Simpson came along and he said, hey, I can do even better. I can get a more accurate estimate than even using trapezoids. If you're interested in how he came up with that, feel free to look in our book. It's in there, or you can Google it. But we're not interested in how he got it. We just want to be able to apply it. This will always be a little more accurate than the trapezoidal rule. Okay, so Simpson Rules says this. We're going to do the same problem. N has to be even for Simpson's. We have to do b minus a again. So what's 3 minus 1? It's going to be 2. We have to do 3 times n. Again, we're using n as 4. So 3 times 4 is going to be 12. So that's 1/6. Now, I'm still going to be doing the same y values because I'm still going from 1 to 3 with n equals 4. I would do 3 minus 1 is 2. 2 over 4 is 1/2. But I already came up with this, so I don't really need to do it again. I can just recopy it. What if I couldn't come up with this chart on my own? What else could you do? Yeah, your calculator would come up with this chart for you. Watch. I can put this function in. I can go to my table setup. I want to start at 1. I want it to go by 1/2. And it'll give me all these values. 1, 2/3, 1/2. 2/5 is 0.4, 1/3. Okay? All right, so I've got the 1/6. So now it says I have to do my initial y value, which is 1, plus 4 times my next one, which is 2/3, plus 2 times my next one, which is a half, plus 4 times my next one, which is 2/5, plus, now look, the last one, do I use any coefficient in front of the last one? Nope. So it's just going to be plus 1/3. So see the pattern for Simpsons, how it goes, the coefficients 1, 4, 2, 4, and it would keep going that pattern, 4, 2, 4, 2, 4, 2, 4, forever, depending on how many ends you have. All right, so now I would use my calculator. So I'm going to have 1/6 times 1 plus 8/3 plus 1 plus 8/5 plus 1/3. And that gives me 1.1. So we can see both of these are pretty close to one another. Simpson's claims that his is more accurate than that one though. So now let's use our graphing calculator. I cannot actually integrate this. It doesn't work, so I have to use my calculator. I have in my 1/x. I go to second trace, calculate number 7. Oh, I gotta let it finish. Sorry, I went too fast for it. I have to let it graph first. Okay, second trace, calculate my integral from 1 to 3. And this is what the answer is for it. It's 1.099. That's the true area. So you can see this was a good estimate, this is a better estimate, and this is an even better estimate. But see how close they all are. And guys, here's what I always see on the quiz. People do this on their calculator, and they get this answer, and then for this answer they have something like 11.9. I mean, guys, you know that's not right. These two should be very close to this, right? So if you get something that's really far away from this, you need to go back and figure out where your mistake is. You probably just pushed the wrong button, or you figured out a wrong y value. Okay? So check that. All right, so let's practice here again just with one little concept. So what if we're going from 3 to 5, and we'll say again n equals 4 for some function. What would be the values that we would have to use for x if n is 4, so I have to get 4 intervals between 3 and 5. What would be the first one I would check? 3. Then what? Then what? Then what? And then what? And then I could just use my table of values on my calculator if I'm in a hurry and don't feel like doing it on my own. I'd have to give you the function, of course, and you plug those in. Okay? What if I had made n equal 8? We're not going to do that, but what if I had said n had to be 8 between 3 and 5? How would that change things? It'd go 3 and then 3 and, not a third, 3 and, it actually would be 3 and a fourth. Because if you do 5 minus 3 is 2, 2 over 8 is 1/4, so you'd have to keep adding on 1/4 every time. So that's how it would be different. We're not going to have to do that, but I'm sure in college you'll have something like that where you have to be more accurate. Okay, any questions over that? That's the last thing. You know, every time we have a quiz, it's over just what's in our packet. So if you want to start looking back at things this weekend, you can. But we'll have our quiz on Tuesday.